Today I'm going to present my poster titled Hardware Transactional Persistent Memory. Recently we have seen an adoption of high-performance transaction processing systems across business and research domains, from machine learning to climate analysis applications. And two technologies hold enormous potential to revive trends in application performance and usher in a new era in transformative speeds. The first is hardware transactional memory, which is an easy-to-use mechanism to support concurrent transactions in volatile DRAM. So easy to use, programming supported by the hardware. The second is persistent memory, which is directly accessed by the processor using load and store instructions fronted by the cache. And persistent memory gives us access to large capacity, persistent data at fast, near DRAM speeds. My research is to combine these two technologies to create a parallelized persistence tier using HTM as our isolation and authenticity mechanism. Currently, Intel announced the Apache Pass system, with availability of the memory of 3D crosspoint chips. And this is an excellent memory, it's large capacity, fast, accessible on the main memory bus. However, we can't just simply remove our disks and plug this in because our applications, which are based in the cache for saving data, the cache can evict out of order and corrupt our in-memory data structures. Also, HTMs typically make all values visible at the end of the transaction. So we can have out of orders after the transaction that corrupt our data. And inside the transaction, if we try and persist, that will also abort the transaction. Another problem is we have to order these transactions. So suppose we have T1 and T2 and T3, which are all updating values. If T2 persists outside of the transaction, and it's subject to a processor delay, now these transactions can be out of order. If any subsequent crash, then T3 would be visible on persistent memory and not T2. So the system should recover to a valid concurrency state, and this can be complex with potentially hundreds of concurrent transactions. So recovery in this case would only recover to T1. My solution, as shown on this poster, is to separate a transaction into three phases. HTM concurrency phase, in which this phase we save the store set into cache memory, and to protect against cache evictions after the section, we do either alias the data so that it crashes into DRAM, or a persistent memory controller so that a crash would be caught by the persistent memory controller. So that update is caught and it's not allowed to percolate to PM until it's safe to do so. The second phase is a logging phase where we persist the store set as a log record into persistent memory. And the third phase is a relaxed durability phase. So a transaction can complete, go on and do other transactions, or it can wait until the transaction ends where it's strictly recoverable. So it's ensured it will be recovered in case there is any failure. So I've built these and it runs on existing Intel hardware. The back-end memory controller can be implemented on or off DIMM, and that has also been simulated to show that it runs near HTM speeds, and that the front-end software is also run on existing Intel machines. And in this result, we have both the controller, which is shown to run 7 times faster than STMs, and the CCHTM, which is our software method, is shown to run 4.5 times as fast. When we implement strict durability, we still see a great performance increase over the green shown there, which is the transactional memory systems. So we've currently testing on Intel Optane DIMMs, so existing persistent memory. The software successfully orders transactions for durability on persistent memory. There's a back-end controller that supports the system if desired to allow even more performance, and it outperforms current solutions. Forward work includes hybrid locking, an IBM Power implementation, and distributed transaction.
Thanks for watching my slideshow.